But for now, I will leave you with Jon Butterworth from UCL, who is going to talk to you about the Large Hadron Collider.
Okay, thank you very much. Thank you. It's nice, really nice to be here, and thank you for coming in out of the sunshine to hear a bit of physics. I'm going to talk you through what's going on in Geneva at CERN, which is an experiment I work on based in UCL, and there are many UK universities and others around the world who collaborate there. I have to confess, happy as I am to be here in Guildford, I have a certain amount of Chicago envy. As you'll hear at the end, there's the biggest particle physics conference in the world every 2 years is going on now, ICHEP in Chicago, where there are some results that have been announced today which I will finish this talk with. So this is very up to the minute, although the beginning of it is hopefully introductory enough that you can see where we get to by the end. But this is happening now, basically. And the star of the show is this. This is the aerial view you would get as you approach Geneva Airport, which you can sort of see as a beige smudge there, kind of in the middle of the picture at the top of that yellow ring. That's Geneva Airport. On the horizon is Mont Blanc. You'd kind of be approaching it over the Jura Mountains in France. And you can see the Swiss-French border sort of zigzagging along there. And that, the yellow circle there marks, of course, you don't get to see the yellow circle, of course, the farmers would have objected, but they wouldn't let us paint it, but it marks the path of the tunnel of the Large Hadron Collider. It's about, varies in depth, of roughly 100 meters underground. It's 27 kilometers around, which, for those of you who are familiar with it, is within a kilometer of the same length of the circle line and the right color, so it's easy to remember. And going around it significantly faster than the trains are the two highest energy beams of particles we've ever managed to get together and control in a laboratory. They're both beams of protons, and they're counter-circulating, one in each direction. And they're brought into a head-on collision at 4 points on the ring, and you can see them marked there on the picture, where it says Atlas, ALICE, LHCb, and CMS. And at each of those points, we have essentially the biggest, fastest, highest bandwidth digital camera we know how to build to record what happens when those protons collide with each other. I'm going to talk today to you about results from the Atlas and the CMS experiments, which are sort of diametrically opposite each other on that ring. Atlas is the one I work on. There are other people in the UK actually work on CMS. And while the other two experiments are interesting, LHCb and ALICE, they're quite specialized experiments, and there's good physics being done there. There's a lot of physics you can do with these beams. But Atlas and CMS are what we call general purpose experiments. So, to be honest, when we collide these beams together, we really don't know exactly what's going to happen. That's kind of the point of the experiment. We want to know what happens when these beams collide, and you don't therefore know exactly how to optimize your detector. You don't know what the most important things to measure are actually going to be, so you throw all the technology you can at it and hope it can do everything pretty well. And that's Atlas and CMS. So before I get into the science and technology of that, just to say a bit about the sociology and the politics. This lab, CERN, is a Centre European Recherche Nucléaire, although the official language now is basically English. It was founded about more than 60 years ago in the aftermath of the Second World War to sort of try and rebuild the collaborative open science that had been going on before the Second World War. If you think about it, in the early part of the 20th century, quantum mechanics, relativity, all the nuclear physics, all the advances in physics were coming from Britain and France and Italy and Germany and Denmark and various European countries. By the end of the Second World War, that expertise had been divided and dispersed and had gone, a lot of it, to the United States, some of it had gone east, and Europe really was in a mess. And CERN was part of an initiative. It was independent of anything else. It was set up in the middle of Europe in Geneva to basically try and rekindle that basic science. There's no explicitly commercial idea behind it, and also absolutely no military involvement behind it. It was completely supposed to be for peaceful, curiosity-led research. Just about the last thing Winston Churchill did as Prime Minister of the UK was sign the UK joining as a founder member in 1954. And it's been going since. It costs about €2 a year per taxpayer in the European Union. And for us, of course, slightly more pounds than that now. But it's, we've been paying roughly that into it for, it's actually independent of the European Union, of course, but it's, we've been paying roughly that into it for the last few decades. It started smaller, but it's been flat for the last few decades. But it's been a very steady and long-term investment that's very stable because it's done by international treaty. Whereas, for instance, in the US, the budget is set annually and there's always a big fuss about it. And the fact that there's that stability has allowed it to really succeed, and to the extent that now every country that's coloured in here has some formal relationship with CERN, comes there to do science. It is really the one place in the world where you do this really high-energy physics. So, how do we do it? Well, we do it. This is a picture, engineering blowout kind of cartoon of the Atlas detector. You can see it's got a sort of cylindrical structure, and each of these concentric cylinders is designed to tell us something different about the particles that are produced when you collide these protons together. I'll show you a picture of this in a moment, but when you collide them, there's all kinds of stuff produced there, and you really, the name of the game is to work out what particles were produced, what their energy was, and where they were going, basically. So I won't go into it in huge detail, but the central parts, the central cylinder there is a semiconductor detector, which is there's lots of very smart ways of using semiconductors here. This is a fairly stupid way in that you just leave it doped so that with a voltage over it, so it's actually an insulator, but it takes a very small amount of energy to free an electron and create an electron-hole pair, which means you get a current released, and that means you can tell for a very small expenditure of energy, you can tell that a particle went by, and that gives you the track of the charged particle. Then around that, there's a calorimeter, which in Atlas is liquid argon, but the point is it should be something that's very dense, but also allows light and electromagnetic fields to propagate through it, so that when particles stop in it, you get a shock of an electromagnetic field, and that tells you what the energy of the particle was. And then the big wheels on the outside are there to detect muons, which are punched through the calorimeter because they're sort of like electrons, but heavier. So, but that's the only other thing really to say about that. You can see the beam pipe with one beam of protons coming one way, one going the other way. Most of the protons actually miss each other, but some of them will collide right in the center of that cylinder. The others all go around the ring again and have another, several more goes. And the other thing, just in case you haven't spotted it, there are a couple of people standing on the beam line there and down below, so it's pretty huge. It's basically a cathedral for particle physics, and this is one of the kind of iconic images of this that went round when we were building it. This is from 2005, before it was finished. You can see one of the people who was building it in the middle. The kind of pictures it gives us are like this now. So actually UCL was one of the teams that wrote the software for the event display that you're seeing here. I think if we'd have known that it was going to be shown in so many papers and things when we got the first results, we'd have probably hired a graphic designer as well as some programmers, but never mind. It does kind of work, and if you go to Geneva and you've got a couple of hours to kill at the airport, CERN isn't really very far away from the airport. And if you're really into this kind of thing, you can go and see the Atlas control room. There's a visitor center with a glass wall. You can press your nose against the glass and watch physicists at work, and you'll see these events on the screens in the control room, because they actually do give us some diagnostic information about what's going on underground where the collisions are happening. What you can see in this one is three representations of the same collision there. And if you look at the circular one first in the top, your top left of the screen, that's a slice through that cylinder, and you've got to imagine one of the beams coming from the back of the tent, the other coming from behind the screen. They collide in the plane of the screen, and you see all those lines are all particles produced in that collision. The ones that are grayed out and bending, they're lower energy, and they're being bent by a solenoidal field, and that, because they're lower energy, it can bend them. But the yellow lines are hardly bent at all, and that tells you that they're very high momentum, and they punch right through the calorimeter, which tells you that they're muons, in fact, and they register in the muon detectors on the outside. The smaller image there is the other slice. This kind of more rectangular one is the other slice through the cylinder, and you can see the same two muons there. And if you zoom in on the red dot where the beams collide, then what you see is that mess at the bottom of the screen. And each ellipse there is a source of particles, and it tells you that there wasn't just one pair of protons collided. There were many, about 12 actually in this collision, and we get many more these days. The protons don't come one at a time, because most of them miss, so it would take too long to collect the data if we did that. And in fact, they don't come in a continuous stream either. They come in bunches about 2 centimeters long and thinner than a human hair. every 25 nanoseconds, every 25 billionths of a second. And that actually tells that I'm not particularly good at numbers for a physicist, but I know the speed of light is 30 centimeters per nanosecond. And if you think how big the detector is, that tells you that these particles, even if they're traveling at the speed of light, do not have time to exit the detector before the next lot are coming, and then the next lot, and then the next lot. And that's even before they start reading out, we start reading out the detector and getting the signals down the cables, also at the speed of light. We have basically an office block full of computing next to this downstairs. Then there's a tier 0 computing center at CERN, which is another 2 or 3 office blocks full of computers. And then it's farmed out around the world on a computing grid, where there's a tier 1 centre in every major collaborating country. The one for the UK is in Harwell in Didcot in Oxfordshire. And then it gets sent to tier 2 centres, which are basically universities, and finally ends up on our laptops and we do physics with it. So when it's running, that's going 24/7 all the time, and there are people on shift all the time doing that. And all the data is shared with everyone on the collaboration. The first paper we wrote based on this was 4 pages long, physical review letters, unless you included the authors, in which case it was more like 20 pages long, because there are 3,000 authors on each of these papers. Sociologically, that's a bit tricky because you worry about people getting the credit for the work they do. On the other hand, if we argued about who went on which paper, it's such a close-knit collaboration that we would never publish anything because we'd spend all our time arguing about the author list. So we essentially give up and put everyone on it. Okay, so why do we want to go to high energies? It's actually, obviously going to high energies is expensive. The reason the ring has to be so big is quite easy to summarize, but it's basically Newton's laws. The problem with these beams is actually not getting them up to high energy. The problem is making them go around in a circle. The centripetal force you need to apply to make these beams turn a corner is huge. It's higher than anything we've ever needed to do. So this tunnel is actually stuffed with the most powerful superconducting magnets we know how to build. And once you've done that, the thing that limits your energy is how sharp is the corner you want to bend the thing round, which mitigates the huge ring. It's big purely for the same reason that corners on a motorway are gentle, so you don't skid off. It would be bad if these beams skidded off. So that's why it's big. It's big because we want to go to high energy, but why do we want to go to high energy? And I've got a massively sophisticated video to show you to illustrate that. What we're essentially doing with this machine is we're looking more closely at, oh dear, let's see if this is going to work. Bear with me a second. It usually does. Okay. Oh, damn it. Okay, maybe it's not going to work. I'll try once more. If it doesn't, then we'll move on. It's not essential. If I can even work out how to move on now. Excuse me. I'm not sure this video is really worth the effort in the end, but that's not good. Okay. Stop it. The point of the video is only a ripple tank with water in it, and it would be nice if I can show it you, but I can't by the looks of it. Hopefully I can get back to the rest of the slide. Help. It's not displaying. I don't know why.
Yeah, it's coming back.
Is it? Thank you. Great. Okay, so forget the video. What the video was going to show you was essentially illustrating the fact that you can't see things unless you have a wavelength that's smaller than the thing you're trying to see. So what it was I'm going to do the video with my hands, I think. Now. What it was a ripple tank where you've got waves traversing it, and you see if you put a blob in the ripple tank, you will see that the blob leaves a shadow, and the waves you can detect with the screen behind the blob. You could tell the blob was there. You could measure the size of it probably and the shape. But if you drop a second blob in, which is smaller than the distance between the peaks and the troughs on the waves, then it becomes invisible. The waves kind of reform around it, and you can't see it on the screen. And that gives you an idea of what's going on in these experiments. What you would see on the video then is that they increase the energy, they ripple it faster, and they shorten the wavelength, increase the frequency, and at some point, the smaller blob becomes visible again because you've increased the resolution by increasing the energy. So the point of that little demo was to say that we need to go to high energy because high energy means high frequency, and that means short wavelengths. Now, so for instance, radar has got wavelengths of meters. It's great for seeing ships and planes, but if our eyes were sensitive to radar, we wouldn't be able to see each other. Our eyes are sensitive to hundreds of nanometers, so we can see fairly fine detail. If you want to see smaller than that, you use X-rays or electron microscopes or something. And you can think of the Large Hadron Collider, these particle colliders, as essentially the end of that chain. Basically, it's the most powerful microscope in the world in the end. And that's by virtue of going to the highest energies, which means the highest frequencies, which means the shortest wavelengths. So what do you see when you do that? This is what you see, this sort of Lego Minecraft version of the standard model. This is, as far as we know, these things are what everything else is made of, and these things themselves are fundamental. That is, they're not made of anything else. All that means really is no experiment we've been able to build, no matter how closely we look at them. We've never been able to break them. We've never seen anything inside them. We've never seen any internal structure. So in our theory and for all practical purposes, they're infinitely small fundamental particles. The red stuff at the top are the quarks. You see the up and the down quark, which are what make up protons and neutrons in different combinations. The electron is below them, and it has a neutrino with it. Neutrinos don't interact very much, but they're produced in beta radiation, beta decay. They're also produced very copiously in the sun. There's a lot of them in this room, but they don't make much noise. That column, actually, I've just described with protons and neutrons. I've just described everything you need to make an atomic nucleus, and you add the electron, then you've got the whole of atomic physics and chemistry and the rest. So it's a bit of a puzzle, actually, that is copied again 3 times. You've got the charm and strange quark and the muon, which I mentioned earlier. You saw those yellow lines on the collision diagram. And then the top quark and the bottom quark and the tau lepton, and they have neutrinos with them as well. And then the purple stuff on the other side is how these guys interact with each other. So the photon is what you're seeing me with now. It's the carrier of light. It's also the carrier of the electromagnetic force. It is the electromagnetic field, if you like. Then the gluon, the G there, is what sticks the quarks inside protons and neutrons and sticks them inside the atomic nucleus. And then the W and the Z carry the weak nuclear force, which is a bit of a tricky one to describe because it's so short range, it never really gets outside the nucleus. So it's a bit esoteric. On the other hand, it's the only one that the neutrinos experience, and it's also absolutely essential in the processes that keep the sun going. So that's why neutrinos are produced in the sun. So it's kind of important, even if it's not that obvious in everyday life. So I'm going to show you the data. So there's a problem that comes with this, though, and that's this grey blobby thing in the background, which is it's quite hard to see how something that's infinitely small can actually have mass, can actually have substance at all. And for instance, the Z and the W on there are about 90 times heavier than the proton, which is very hard to imagine when they're supposed to be infinitely small. And that was a problem that was realized even before we knew about quarks. It was realized that it's not just a kind of intuitive problem that it's hard to give such small things mass. It's actually a problem built into the mathematics of the theory behind all this. And even in the early 60s, before we discovered quarks, people were worried that this was going to be a long-term problem, a fundamental problem with the theory. And there were Francois Englert and Robert Brout in Belgium and Peter Higgs in Edinburgh were worrying about this and came up with a solution, which was to fill the whole universe with a new energy field, because that's the kind of thing theorists can do, and say that the mass is not something the particles have intrinsically, really. It's something they get by interacting with this field. And by a sort of mathematical sleight of hand, that made the whole having mass thing work, made the mathematics of the theory consistent. Actually, Brout and Englert got there first by a few weeks, independently of Peter Higgs. So you might wonder why there's a big H on there and why we talk about the Higgs boson. And that's because he was a bit lucky, actually. He wrote a term a bit more explicitly in his paper, which is to do with the experimental evidence. I don't know about you. I'm an experimentalist, and I don't know about you, but filling the whole universe with a new energy field is a bit of a leap just to make the maths come out right. So I'd like a bit more evidence for it. Now, a field like the electromagnetic field or whatever is what physicists use to describe it, something that just fills space and has a value everywhere. So there's an atmospheric field in this tent, which has a temperature and a pressure at every point in the volume of the tent. And in the same way, the Higgs field, if it's there, will have a value at everywhere in space. And detecting whether that field's actually there or not, it can be tricky. I mean, for the air in the tent, it's easy enough. If there was no air in the tent, not only would you not be paying much attention to me, but you wouldn't actually be able to hear me, because one of the reasons we know the field is there is that sound waves are traveling through it. There's a pressure wave traveling from my mouth to your ear, or from the speakers to your ears, which is evidence that the field is there. Now, it turns out that's the only way we know how to prove whether the Higgs field is there or not. Is to basically hit it really hard and make a ripple in it, make a wave in it. And that ripple, it's actually a quantum ripple, it's a quantum excitation, basically makes it a particle. That ripple is the Higgs boson. And Peter Higgs wrote that a little bit more explicitly in his paper. That became the experimental linchpin of the whole thing, which is this whole theory of mass is right. Then in the end, if we hit the universe hard enough, we should make a ripple in it, which is the Higgs boson. And that's one of the things the LHC was designed to do. So I'm going to show you the data that shows that that was right. This is the most technical bit of the talk. I'm going to show a couple of Feynman diagrams. Don't panic if you don't like them, come back in a minute. But these are the cartoons that show us that we use to represent the calculations of a collision. So we're talking about colliding particles together. We predict probabilities that a given thing will happen, and then we compare it to the data. We just count how many times it happens, and if it's right, the theory wins, and if it's wrong, we win. For every term in this, every line and dot in this cartoon, there's a term in an equation that goes with it. But what you can see there basically is an electron and a positron coming in, annihilating, making a photon, which is a wiggly line in the middle, and then decaying back again to an electron and a positron. And there are three bits of physics that come into play here that actually are in apparent contradiction with each other. First one is the only equation in the talk, I think. First one is energy is equal to mass times the speed of light squared. Fine, it's true. The other is that energy is conserved. So there's a lot of energy goes in from the collider. And there's a lot of energy goes out again because you measure it in your detector. So there must be a lot of energy in the middle, in the photon. And then the problem comes from the fact that the photon has got zero mass. And c squared is a big number, but if m is zero, then the energy in the middle should be zero, which would mean that energy is not conserved, which means physics has a hissy fit. So how do we get around this? We get around this by the fact that this is quantum mechanics, which is slippery. And in fact, all we do is measure what goes in and what comes out. So the stuff in the middle is, in a sense, not real. You need it, because if you don't put it in there, you'd get the wrong answer in the equation, but you never actually measure it. It's a kind of possibility in quantum mechanics. And in fact, you have to sum over all the possibilities in the middle of that diagram to get the right answer. And because it's not a real particle, then, the photon is allowed to have the wrong mass. So it doesn't have zero mass. Now, there's a remnant, I know this sounds a bit odd, is that there's a remnant of reality in this, because the further away it is from its correct mass, the less likely the thing is to happen. But it's still there, that it can have the wrong mass. It won't be a zero probability if it has the wrong mass. So this looks like a bit of a silly experiment to do. If the energy is high, the photon has to be a long way from its mass, so it's actually very unlikely to do this. But there's another particle in there called the Z boson, which you saw earlier, which does have a mass of 90 times the mass of the proton, roughly. So if you tune your energy up right, you can make those three things hit the sweet spot. You can say the Z has the right mass, E equals mc squared, and energy is conserved, and they all work at once. And then the probability will be very high. So this plot shows that, all those things I just told you. You can see at the far end, the probability, so what you've got on the vertical axis is the probability of it happening in some strange physics units. And what you've got along the horizontal axis is the mass of the wiggly line in the middle. And you see the probability is very high on the far side. The photon would have roughly the right mass there, nearly zero. As you go up and up in mass, it drops very, very quickly. That's a logarithmic scale. And then there's this huge peak where the Z boson is, where suddenly the Z has the right mass, and you see this kind of resonance appear, that the probability peaks where all those three things come together and the particle works. And that's a very generic feature of doing physics at colliders. If you see a peak in a probability, that probably means that in all the mess of possible Feynman diagrams you might have describing the collision, there's a new particle popping up, and that's what's causing the peak. So that's how we look for the Higgs boson as well, not in precisely this experiment, but in one rather similar. We look at what the Higgs can decay to. It decays very, very quickly if you produce one, so you can't kind of get them in a jar and keep them for later. You have to see what it decays to, measure what it decayed to, and work out what its mass might have been. So one of the possibilities that it can decay to is a pair of photons, and those are those yellow blobs. You see in the green ring there's a couple of yellow blobs, not looking terribly impressive. But if you look at the little histogram on the side of it, you see that they've got a huge amount of energy compared to the rest of the event. And the green bit at the bottom there, that's just zooming in on the yellow blobs. You can collect, you say it's 2 photons. It might have been a Higgs, it might not. We've no idea. But what we can do, because we can do some relativistic kinematics and we've measured their energies, is we can say, hypothetically, if it had been a Higgs, what would its mass have been? And we can plot that mass in just the same way as on the previous plot. And here you go. This is 2 years of my life. You can see the date ticking away in the top corner there. This is the horizontal axis is the hypothetical mass of a Higgs, if it was there, the mass of the pair of photons, if you like. Number of times it happened on the vertical axis. Lots of statistical noise, but as you get more and more data, that dies down. And then in the middle, you have a little bump that doesn't go away. That's the Higgs boson. Now, it's not super impressive, I realize, but it's kind of telling us a lot about the way nature works. I remember on 3rd of June 2012, which was the day before we announced the discovery, I was in CERN watching the data put together by our spokesperson, Fabiola Gianotti. It was really exciting to watch. And then I had to go to London because I was head of the UK bit of the experiment, and we had all the politicians in Westminster to talk to. And my opposite number on CMS was also there, Jim Verdi from Imperial. And just before that whole thing kicked off, he showed me his top secret data, and I showed him mine. And this is what they had. And this is the same bump in the same place. And I honestly thought that I believed our data. But I must say, I got a certain wrench in the gut when I saw that the other guys had confirmed it. I think it's quite surprising because we thought we'd done all the checks we could, and I really thought I believed that Atlas had found the Higgs, but it wasn't until I saw CMS had it too that I really actually at some level believed the result, where nature was telling us something very, very profound about the way the universe works there. Remember what that is. That bump is a sign that there's a new particle entering in these Feynman diagrams, which is the excitation in the Higgs field, which is the evidence that this energy field that fills the universe is really there, which tells us that we actually understand where the mass of fundamental particles comes from. So it's quite a big deal for a little bump. So where are we now? Well, I sort of lied when I said that this is what everything in the universe is made of. One obvious thing that's not there is gravity isn't included. This is beyond the standard model. It gets worse, because even if you include gravity, okay, we have a theory for gravity, it's called general relativity. If you include that in and the standard model, then you allow those two theories to coexist, which they don't do very comfortably anyway, but if you do, then you start looking around in the universe and you find out that even with those two, we don't understand how galaxies move, we don't understand the distribution of matter in the universe. We say there's something else out there called dark matter, but we don't know what it is. It doesn't seem to be made of any of the fundamental particles we know of. There are various other things. We don't know why the universe is predominantly matter and not antimatter, because when in a collider, we typically make equal amounts of both of them. So there are a bunch of open questions. We're in an odd situation. The standard model of particle physics is sort of complete and internally consistent, but it's obviously not a theory of everything. So we're looking for clues that will give us a bigger and better theory. And so we go onward. I'm just going to skip over these. But we're looking for bumps all the time and excluding them. Until yesterday, or this morning even, I would have been showing you this and saying, oh, I wonder if this is a bump there. So you see there's a bump at 750 GeV, similar kind of plot to the ones I've been showing you before. It's not statistically completely significant, but it's in Atlas and CMS and maybe indicative of something going on. Unfortunately, it's gone away as of today. Oh, I thought I had, oh yeah, sorry. I've lost the slide. Oh dear. I had some data that was shown actually today in Chicago, but unfortunately it's an update on this which shows that particular bump has gone away, which is a bit sad. There's another one which hasn't gone away yet as far as we know, which is this one, 2,000 times the mass of the proton, statistically marginal. You saw the animation, you saw there are all kinds of noise and bumps and things, and most of them go away. So we've got all kinds of stuff like this going on, trying to not get too excited about chimeras in the statistics, but on the other hand, trying to take them seriously if they happen. And if they do happen, they're beyond the standard model. There might be a clue to some of the missing pieces that we don't understand in there. The good news is that the Large Hadron Collider is working extremely well. What you see here, the blue line is the data we got at lower energy that we discovered the Higgs with. The pink line that's going up above it now is what we're doing right now this year at very high energy. If that carries on, then a lot of this statistical noise will die away, and if there are any bumps there, we'll probably find them. So it's good. This is going on right now. This is where the data I was going to show you, but seem to have lost, has just been shown today, this morning in Chicago, so just about an hour ago, in fact. Unfortunately, what it showed was one of those bumps vanished already, but there's other stuff going on there. It's a very exciting time, actually, to be doing physics. So I was going to finish there. Just one thing I will say, since I saw the end of the previous talk, which was all about miniaturization of computing, or one of the things it was about was miniaturization in computing with the pi zero at the end of it. We don't seem to be doing that. This is a picture of the Large Hadron Colliders, the little ring on there, and this 100-kilometer dotted line is what we might build next. There's a view of it from the Jura Mountains here. But actually, that's not the full story. It's not just about digging bigger tunnels. And what you see in here is actually an accelerator on a chip. That's a human finger it's on, and this chip can get higher accelerating gradients than anything we have in the Large Hadron Collider. It's got nanoscale serrations in there, which if you fire a laser transversely to it will give you really high electromagnetic accelerating gradients. So if you strung a lot of these together, you could probably get the energies of the LHC in about 30 meters rather than 30 kilometers. There's always a catch. The catch is you need very big lasers to fire transversely to it, but it's just to give you a flavor of the fact that it's not just about building bigger and bigger tunnels, it's also about being smarter with the technology, and that's something that goes on a lot as well at CERN and at UCL. And with that, I think I'll finish, and I've got time for some questions, if you like.
If you have questions, please raise your hand, and I will bring the mic to you.
Just a quick one. You talk about using protons. Wasn't there talk at one stage about using other nuclei as well, lead, etc., to take the energy up for the higher energy for the same speed?
Yeah, so I'm trouble hearing because of this, but you're saying using other nuclei and other particles, yeah? We do. So it's called the Large Hadron Collider, not the Large Proton Collider, because we do actually put lead atoms in there, lead nuclei in there sometimes. They get to higher energy because they've got a higher charge, so you can accelerate them more. On the other hand, the energy per nucleon, if you like, is not as high. So in fact, they do slightly lower energy physics, bizarrely. The whole game is about density of energy, really, not the total energy. So the density of energy in a lead-lead collision is actually lower than a proton-proton collision, so they won't find the Higgs for you. But what they do is you create this stuff called quark-gluon plasma, which actually is more of a liquid, it seems, but which is a kind of another stage of the early universe. It's a kind of exotic form of matter, where quarks and gluons are essentially free, rather than bound inside hadrons and hadrons and bound inside hadrons, protons and neutrons or whatever. So there's good physics you can do with that, but paradoxically, although the beams are higher energy in that configuration, the resolution, if you like, that you're accessing is actually lower. The energy is lower. So, and there are also colliders with electrons, which get to quite high energies, but not as high as protons. And there are discussions about muon colliders, which would potentially be very nice, but have technical challenges, shall we say.
Any more questions?
Seems to be one at the back there, I think.
Is there someone? Raise your hand. Okay.
Just a question about weakly interacting particles like neutrinos, for instance, right? So I understand that that they are streaming through our bodies all the time, right? So you can't shield for them, right? So they must also be interacting with the beam at some point. Is that something you can you do observe, or is it?
We have observed. We don't observe neutrinos in the LHC. We indirectly know they're there because we surround the beam with a detector. So you can, from the fact that something's missing, you can deduce that probably you had a neutrino. So there's an imbalance in momentum in the final state of the collision. So in that sense, we do measure at least missing energy, which is then probably neutrinos, and we can test that. It might actually be dark matter, so we're always alert to the fact that we might have created a bit of dark matter and it fakes a neutrino, because that also doesn't interact with the detector. There are dedicated neutrino experiments. I mean, the trick with detecting neutrinos is to have a lot of detector and a lot of neutrinos, and then eventually you'll see one or two of them. So there's an experiment actually in Chicago firing a neutrino beam from Fermilab through Minnesota into kilotons of iron scintillator, and they get a few neutrinos a day when they're firing billions and billions and billions of them. And there are also experiments that did detect the neutrinos from the sun. There was a big puzzle for a while. There didn't seem to be enough neutrinos from the sun, and they built detectors to check that, and in the end they found out that's true. There were not enough electron neutrinos from the sun, but they were changing type on the way here, which was an important clue as to the makeup of the standard model and the fact that neutrinos have mass, in fact. So neutrinos are extremely interesting, but we don't do a great deal with them at the LHC because we don't make enough of them. You need a lot of them to actually do anything with them.
Any more questions?
So if neutrinos don't interact with anything, how do you make them into a beam? I know it's not in CERN, but it sounds interesting.
Yeah, they go in a straight line, that's for sure. You don't bend them with a magnet. What we do is you start with protons, in fact. So you smash protons into a target of some material, some atomic material. And one of the hadrons that's really copiously produced when you do that, when you smash a high-energy proton beam in, is a pion, which is a quark and an antiquark pair. And some of them are charged. So you take the charged ones of those, you put them in a beam, you collimate them, you point them where you want them to go, and then at some point they decay into a neutrino and an electron or a muon. And you rely on the fact that the energy, you've pointed them in the right direction before they do that. The mass of the pion is quite low, so the neutrino will carry on in roughly the direction the pion was going in. And then so you have this kind of beam of neutrinos fanning out. But definitely, once you've got a neutrino, it's going to go the way it's going. It's not going to be changed in direction. You can't control it. So.
And there was maybe one last question. Oh.
So, any hypothesis on what the 2 TeV peak could be if it's real? And what's the name of that accelerator on the chip?
The accelerator on a chip, it's not been built as a working accelerator yet. I think there are prototypes for low energy beams for medical applications, but there's no working particle physics thing. So I don't know, I'm afraid, the name of it. It was built by Stanford Linear Accelerator Lab, so you can probably find out from there there's a technology group there that did it, but I don't know whether they've named it or anything yet. The other question, what was the other question, sorry? I can't, sorry.
The 2 TeV peak.
Oh, yeah, sorry, I've got a memory like a goldfish. The 2 TeV peak, it looks like what it is, the way we see it there, if it's real, is it's in a pair of W or Z bosons. So it's some really heavy thing that decays to a pair of W and Z bosons. There's no off-the-shelf theory for that. It's not obviously something like supersymmetry or whatever, but there are models. There are models even with extra space-time dimensions where it's some kind of higher geometric excitation of one of the particles we know, really out there stuff. But it doesn't actually. If it's real, then it will kind of throw the cat among the pigeons amongst the theorists, because it's not one of the things they're waiting to tick off. It's a bit unusual. So with the diphoton bump, even though it's now gone away, in the brief period it existed, we had about 500 theory papers trying to explain it. If the 2 TeV bump doesn't go away, then there'll be a similar number trying to explain that as well, if not more. That's kind of the joy of being an experimentalist. You write one paper and then it gets cited 500 times by people trying to explain it. There you go.
Hi. Sorry, just from an engineering question. Atlas is a very big machine, and you've got quite a lot of energy going in there in that interaction. What kind of maintenance do you have to go to, or what damage does it get?
What kind of what? Sorry?
What kind of damage does the detector get, and what kind of maintenance?
What damage?
Yeah, what kind of maintenance do you have to put under?
Yeah, we have to take, particularly for the bits at low angle to the beam and close to the sensor, you have to take radiation damage into account. And there was a lot of R&D done before we built it to try and make sure that the front-end electronics would be robust against that. There's this kind of what they call a Lazarus effect, where you sort of anneal it in a test beam, and it goes through a performance dip where you get the defects build up in the silicon and it disrupts it, and you get a very bad signal-to-noise ratio. But then at some point, it seems to anneal out and recover some of its initial performance. So everything that was put in there went through that process, basically, or at least the silicon did, to blast it like that. Even so, there's a lifetime, and if we want to carry on taking data beyond about 5 years' time with it, we'll probably have to replace most of that silicon in the middle of it. And we've already had to replace some of the electronics that's very near the beam pipe, kind of quite a distance from the collision, but at very low angles, so there's a lot of very high flux of particles there, and it really does cause damage. So it's a serious issue. Although CERN is explicitly non-military, it got a little iffy at some point because a lot of those requirements for fast electronics as radiation hard are actually common with the nuclear industry. Some of it is civil and some of it's pretty uncivil. So we had to watch what we were doing there in terms of negotiation, but there's interesting stuff there.
We still have time, but for questions, but if there's no more...
Maybe we should stop here, but I'm going to go over to the info tent. And if anyone wants to carry on talking, they're welcome. And also, this is a book I wrote about the Higgs discovery, and I've got some of them for sale if you're interested as well. So, okay. All right, thank you very much.